Check it out now, y'all.
NanoHUB-U, online instruction.
Welcome to the last module for this week, and in a way it actually also concludes the things we have been talking about for the last 4 weeks. We have been talking about this NEGF method, and this last week, that is this week, we talked about how it is applied to spin transport problems. But in general then, like next week we'll be talking about something very different. It's about second law information. It's not about NEGF. So this module kind of concludes this section, all these 4 weeks in a way. And so I have a few different comments to make. Just to remind you then about spin transport, as you see, that's something we talked about in the first part of the course. And at that time, we didn't have this quantum transport method. And we discussed a bunch different types of phenomena that you could understand just in terms of up and down, what we call maybe red and blue, just two types of spins. And what we have now done using NEGF is also brought in these subtleties that are associated with the idea that there is not just an up and a down, but you could also have spins that point in intermediate directions. And something in this direction is actually a linear combination of an up and a down. So if this is the z direction, something pointing along x is like a combination of plus z and minus z. And this is the thing that the quantum method incorporates into it. And the problems we talked about, I guess the first problem, even in the first part 1 of the course, we talked about 2 terminal devices. That is where you have 2 magnetic contacts. And these are devices that have found applications. There are real devices being built. And what I showed in the first module or 2, I guess, is how one could set up the NEGF equations to discuss problems of this type. Now, one thing I should mention in this context is that in order to describe this full spin and magnet system overall, one should actually use a coupled model where you have a transport model that tells you how spins are transported and an LLG, something we didn't talk about at all in this part of the course, this Landau-Lifshitz-Gilbert equation, which describes the dynamics of the magnets. So there are some devices where the magnets don't turn, they are just fixed. In that case, you don't need the LLG. You can assume that the magnets point in a certain direction, and then whatever we discussed, this NEGF tells you that if you give it the voltage and the magnetization of your magnets, it will tell you how to calculate the current. Actually, you can also calculate the spin current. That is something, again, I didn't go into in my lectures, but it's in the notes. So you could calculate what the spin current would be as well. Now, if the magnets actually turn in the process, then you need something that describes the dynamics of the magnets as well. And that's this LLG equation that we discussed a little bit in the first part of the course, but we didn't get into here in this part because, again, this course is largely about the transport problem, and we wanted to focus on the NEGF. And for the LLG, it's like you put in the spin current, and what the LLG tells you is how the magnet turns. And in general, those 2 things have to be done, solved consistently. Now, the second type of problem that we talked about were these non-local things. Non-local meaning, and this is again in part 1 as well, towards the end of part 1, we started talking about non-local structures where the current runs in this part of the structure and you measure a voltage somewhere out here. Because when the current runs here, these spins diffuse away. There is this spin accumulation in this region, and you can measure a potential. And that's where I guess in the first part of the course, we had magnets that were either in the direction of this magnet or opposite to that direction, whereas now we can talk about magnets in arbitrary directions compared to the the input magnet. And this is the part that we discussed how you could use NEGF to model these. And one of the interesting problems that I think I went over in a little more detail in the tutorials that you should also look at is that now there are experiments showing that, let's say this magnet is in a certain direction, and you can measure the potential with this magnet. And of course, if the magnet is in the same direction, you'll measure a high potential. And if the magnet is in the opposite direction, then you'd measure a low potential, and it would oscillate like so, as we discussed. So in principle, you could measure an oscillating potential if the magnet were rotated, but often the experiments are done keeping the magnet fixed and actually rotating the electron itself. That is, from here, electrons are injected as, say, upspin, but by the time they get here, they could have rotated. How would they rotate? Well, we discussed these two possible mechanisms. One is with a magnetic field, because anytime there's a magnetic field, the spin wants to rotate around it. And we discussed how we understand that, how we model that. And another possibility is a purely electrical way of rotating things without any magnetic fields. That's using this spin-orbit coupling. And there again, you should look at the tutorials where we discuss some of this and the homework problems. And for spin-orbit coupling, it's like there is a gate here, gate potential, with which you can change that spin-orbit coupling and thereby change the potential that's observed here. This is a much more difficult experiment, and at this time I think I know of two experiments which show this effect actually, where a potential here changes the potential that you measure out here. And this is the effect that is often referred to as spin transistor, although there are many other versions now that people talk about. But this is usually what we refer to as a spin transistor, and I should remind you that this is really transistor in a very loose sense of the term, in the sense that one voltage can control another. That is, if I change this voltage, the spin-orbit coupling changes, and as a result, what you measure out there changes. So you could draw something like a V input, that's the potential here, and the V output, and let's say it will change in some way. Now, of course, at this time in the experiments, the change in the output is much less than the amount of voltage you have to put actually at the input. And so, it really, strictly speaking, shouldn't be called a transistor. I mean, you're not getting any amplification of any kind, really. And whether such things with different materials, with different ingenious structures can be observed in future, well, that remains to be seen. But at this time, you see, there is no good reason to call it a transistor. And then there are also experiments where instead of having a intermediate thing here, people just change this voltage and look at the change in the voltage over there. And there also, what you'd observe is usually a change in this output voltage. And if this is a small magnet, then actually as you increase this voltage, at some point, this magnet can flip. Like if it was originally anti-parallel to this, at some point it can flip and come in the same direction. And then people see things like something that changes like so. So where the input and the output have sort of a hysteretic relationship. Why? Because, well, the output was increasing, and once it's increased enough, the magnet flips and becomes parallel. And once it's parallel, you measure a much bigger voltage. And then when you reduce it, again, at some point it flips back, and then you measure a lower voltage. So such things have been observed, though not in semiconductors, but in copper channels. But here again, to call it a transistor, of course, the change in output voltage needs to be bigger than the change in input voltage, if you will. And that isn't the case at this time. And another interesting possibility here that we have actually discussed in some publications, but I won't go into all this, is that, well, usually you think of the voltage as your signal and the spin as something that is internal. But supposing we think the direction of the magnet as the signal itself. What I mean by that is instead of VO and VI, supposing we were to look at the output magnet direction, MO, as a function of MI. Well, then you'd see that the change in the output magnetization is comparable to the change of the input magnetization, in the sense that if I take this magnet and turn it, that magnet also, at some point, if there's enough voltage here, will turn. And then you could say, well, you actually have gain. So that is part of the thoughts here that people have in these directions in this area now, is that maybe in order to have a spin transistor, you should start thinking of systems where even the external information is not in the form of voltages, but in the form of magnetizations. So that you have magnets that contain the information, they inject spins, and these spins go and turn another magnet. Okay? And no need to convert anything into voltage. That magnet in turn then injects spins, turns a magnet, and so on. So you could have things that operate purely in this spin magnet domain without going back into charge voltages and so on. But all these are really areas of current research, and it's hard to tell where things will eventually go. Okay. Now the other point I wanted to make is the connection between what we talked about in part 1 of this course and how we talked about spin in part 2 of this course. If you remember, in part 1, we described the propagation of spins using a diffusion equation. Whereas, in this part of the course, we talked about spins using these NEGF equations. And what you might wonder is, what's the connection between the two? They look totally different things, you see? And this, as I said, can describe spin, how spins diffuse quite well. As long as you can talk about things in terms of just ups and downs and don't have to bring in these intermediate directions. But then what is the connection between this and this NEGF? Well, to see that, let me first tell you that this remind you a little bit about the diffusion equation. If you remember, the equation looks something like d2n dx2 equals 0. And you could take that and, let's say, discretize it. So if you had a discrete lattice with points like this, where you have p, p minus 1, p plus 1, then d2n dx2 actually can be written as something like this. So you could write it as n of p plus 1. Actually, let me write it over here. To write it as n of p plus 1 minus n of p divided by a. So let me get a better pen here. So this is, you look at the electron density here, and you take the difference and you divide it by this distance a. So that's like dn dx around here. That's that. And from it you can subtract the dn dx around here. And that would be like n of p minus n of p minus 1 divided by a. So this would be like the dn dx here, and the second term would be like the dn dx over there. And d2n dx2 is obtained by taking the difference between the two. Whatever dn dx is here minus whatever it is here. Okay? And so that's what I've written here. And then divide the whole thing by a. So this is the standard finite difference method, actually it's called, of turning that differential equation into a sort of difference equation. Right? And you could collect these terms together and write it as something like this. and you're putting that equal to 0. And another way of thinking of this same equation, you see what I tried to show you is, you start from this diffusion equation, do this finite difference approximation, then you'd get an equation like this. And since this is equal to 0, that's like saying that this np plus 1 plus np minus 1 is equal to 2np. Now, another way to justify this is by saying that, well, basically you have these electrons which are jumping around. And in a certain length of time, half the electrons here jump to the right, and another half jumps to the left. And so if I stand here and I look at what the electron density in unit P is, it will be like half of what it was in P plus 1 and half of what it was in P minus 1. So from that point of view also, you could come to an equation like this. Now, the reason I'm mentioning this is, of course, because not that I want to talk much more about diffusion equations, but what I wanted to show you is how the NEGF equations could be put in a form that kind of looks like a diffusion equation. See, that's the point I'm really trying to make. And to see that, let me explain. The way it would work is, you see, NEGF equations, as you remember, is Gn, that's this matrix, which is like the electron density, is equal to Gr, and then there's sigma n, and then there's Ga. And this sigma n, as we discussed, I guess last week when we were talking of dephasing, we said that the sigma n could be written as some constant d0 times Gn. And there, we talked about two types of dephasing. You see, one where the d0 is a constant. So if Gn is a matrix, the sigma n also is just the same kind of a full matrix, just like Gn multiplied by a number. But then there was the other type of dephasing we talked about, the one that also relaxes momentum. And for that one, d0 times Gn, you only keep the diagonal elements. So let's say we are talking about that one. Okay, so it's just the diagonal elements. So then you could write, so supposing I want to write the Gn at the location p comma p. So, now this is a matrix multiplication. So I should write here P comma Q, and then since this has only diagonal elements, I'll put Q comma Q, and then the last one has to be Q comma P. And of course, by the rules of matrix multiplication, you have to sum over all the Qs. Right? So I won't write a summation here, not to clutter things up, but you have to sum over all the Qs. But the indices, as you know, the way it goes is P, Q, Q, R, but then since this is diagonal, it's Q, Q, and then it goes from Q back to P. And then overall, there is a constant in front, some D0, let's say. Now, the point is that this quantity is like N of P. This is like the electron density at location P. And this, I guess, is d0 times Gn. Sorry, this was Gn because sigma n is like d0 times Gn. So what you get then is N of Q times a quantity that is like d0 Gr P comma Q times Ga Q comma P. And then there is, of course, summed over all Q. So the point that I'm trying to make is, this then starts to look a lot like a diffusion equation. Because diffusion equation, if you recall, what I tried to show you a minute earlier, is that this d2n dx2 equals 0, you could reduce to something of this type, where n of p is equal to n of p plus 1, n of p minus 1, terms like that. So the electron density at a particular point is composed of a weighted average of other points, and which you can view as a sort of random walk, that the electrons at P came from some electrons from P plus 1 which hopped over, or some that from P minus 1 that hopped over. And you could say the same thing here. It's like N of P is this electrons at Q that hopped over to P. And the fraction that hopped over, that's what is described by this quantity, this product of these Green's functions, which has all the quantum information in it. So the point is that starting from the standard NEGF equation, if you went to this picture, you could make it look like a diffusion equation. And of course, this is summed over Q, and in principle, with the diffusion equation, the P only connects to P plus 1 and P minus 1. That is, it's only nearest neighbor hopping. But what we did with the NEGF, of course, for P, P and Q need not be nearest neighbors in general. The Green's function could be extending further out. But then, if you have sufficient amount of dephasing, then often the Green's function also becomes relatively local. That is, doesn't extend too far. Okay. Now, the point I wanted to make next is that, okay, this sort of turns it into a diffusion equation. But supposing we want to keep the spin information. So let us say we have all kinds of dephasing, but all kinds of incoherent processes, but which do not destroy spin. Well, what you could do then is, when you write Gn p comma p, you could visualize it something like this, that you have this lattice, and you have points like this. There is this upspin component and a downspin component, and an upspin component and a downspin component. And you could take this, when I write Gn p comma p, it could be a 2 by 2 matrix at that point. You see, in the up-down basis. So this actually could be a 2 by 2 matrix. This is the p comma p component of that. And similarly, this then could be a 2 by 2 matrix. And so what I'm writing here as N of P is really a 2 by 2 matrix now. And that is also a 2 by 2 matrix. And so it is as if that 2 by 2 complex matrix, that is the quantity that is hopping around. And this thing in here tells you how it hops. What are the chances of hopping to different places? Now, this matrix, of course, we have talked about its interpretation in the past. That is, if you remember, so this 2 by 2 matrix, as you know, can be interpreted as N plus SC, N minus SZ, Sx minus ISY, and Sx plus ISY. See? So it's a 2 by 2 complex matrix, but you could also interpret it in terms of number of electrons, spin in the z direction, spin in the x direction, and spin in the y direction. And so you could turn this into a diffusion equation where what is hopping around is this complex object which carries all 4 of these informations. You see N, Sz, Sx, and Sy. And the diffusion equation that we talked about in part 1 of the course was kind of a simplified version which only talked about N and Sz. The part that you can just think in terms of, up plus down and up minus down. Whereas, what we now have is the full NEGF version, which can give you the full diffusion of this 4-component object, you see. And so, what you can envision for future is devices, where it is not just the charge that is diffusing, but also the spin information. And to conclude, though, I'd like to add one more aspect to this, and that is that you'll often hear this word pseudo-spin. And pseudo-spin kind of refers to the idea that there are other things which are physically not like spin, but can be viewed in terms of 2-component things. And so, mathematically, they are isomorphic to what we have been talking about. See, so if once you have understood this math and mastered it, I guess, you can think of other things that are physically different, but you can use the same math to think about it. So for example, in the context of graphene, you'll often see it, that, I guess, again, this is not something we went into too much in this course, But I did mention that when discussing the energy levels in graphene, the unit cell consisted of these A atoms and B atoms. Just as, right now we are talking of just 1D wires and 2D wires where you have an up component and a down component in each unit cell. So the A atoms and the B atoms could also be sort of viewed as, again, up and down components. See? And you could think of it as a pseudo. So often people talk about, this is quite common in the literature, to talk about this pseudo-spins when talking about wave functions in graphene. Pseudo-spin being, instead of up and down, is like the A and the B. Other examples of this could be, so for example, we talked about one problem I think we did week 2 or week 3, was that if you have a 1D wire and you have a scatterer here and you have electrons coming in and getting reflected, if you looked at the potential, you could see oscillations like this. And of course, this is a problem that if you just thought of electrons as particles, you would have said, well, there is a some positive going electrons and some negative going electrons. And you could think of the chemical potential mu of positive going as mu plus and those of negative going as mu minus. See? So how do you understand this kind of thing, where the mu is actually going down? Because ordinarily you think if current is flowing in a certain direction, chemical potential should just be going down. Well, here also the way to think about it is as if, you see, plus and minus are kind of like these two pseudo-spins. So that is the one going this way and the one going this way. Those are like the pseudo-spins. And at this point, the two spins are in phase. That is, if I looked at the wave here, it would be like 1, 1, in the sense that the forward going wave and the reverse going wave are in phase. That's 1, 1. So in pseudo-spin language, that's like something, a pseudo-spin that's pointing in the x direction, because x is like 1, 1. On the other hand, when you go here, that's when the two are out of phase. That's like 1 and minus 1. As if what has happened is that pseudo-spin has rotated. Why is it rotating? Well, when we talked about why ordinary spins rotate in a magnetic field, I tried to explain that what happens is when you have 1, 1 and you have a magnetic field in the z direction, this one picks up a certain phase, that one picks up a different phase, and the result is the spin rotates. Here also it's kind of like that. When something propagates in this direction, it picks up a e to the power plus ikx, whereas the reverse wave picks up a e to the power minus ikx, and so the overall spin rotates. So these, of course, till you go through it properly and look at some problems carefully, it takes some time to grasp it properly. But the point I wanted to make here is just that once you understand the algebra of spins and this way of thinking about things, you start seeing spins everywhere. And all kinds of things that have the two components, you say, well, it's just like what I learned about spins. And I can use all those thinking to understand it. Although in many cases like this one, it may be much easier to understand it in less fancy language. But it's just that once you get used to it, that same algebra describes all kinds of things. And so often people talk about, of course, spintronics you'll hear a lot about, the idea of how to use spins for information processing. And in that context, you also hear the word pseudo-spintronics. That is, all these various things that could qualify as pseudo-spins. In the sense their math is a lot like spins because they have two components. Or maybe even ones that have more components. But you often refer to these as the pseudo-spintronics. But if you're trying to use it for information processing, I'd say the one thing that we have learned in the last 20 years is that this field of spintronics has really progressed a lot because of this marriage of spins with magnets. You see, because before that, you only had these quantum objects called spins. Whereas now what we know is how to use concrete classical objects like magnets to generate these spins and then use these spins to turn a magnet so that, you can convert this quantum information back to magnets. And I'd say that is what today is very different from where things were 10 or 20 years ago. And so whenever people tell me about, about some pseudo-spin that could possibly be used, my first question always is, that I think about is, well, is there a pseudo-magnet to go with that? Is there something that would let you generate those pseudo-spins and something that would again allow you to take information out of those pseudo-spins?